write an exponential model using a growth or decay factor. So first, let's talk about the exponential model. Now, we're going to use A equals I times the quantity 1 plus or minus the percent to the t power. Now, what do these mean? So A is the ending amount of whatever we're talking about. I is the initial value. So how much do we start with? Whatever we're talking about, what do we start with? Now, inside here is either going to be the growth factor or the decay factor. Remember, growth factor is going to be greater than 1. Decay factor is less than 1. So the whole you plus for growth, you subtract for decay. So the percent is either the percent increase or the percent decrease. T is your time. Now, time could be in days, months, years, millennia, doesn't matter. Okay, it's your time period. So let me even put that time period. Now, one other thing that I want to put out is that this whole piece inside the parentheses is the growth factor or the decay factor. Meaning, if you find that the growth factor is 2, that replaces this whole thing. Just replaces with a 2. Because sometimes we're given a percent increase, sometimes we're given 2 consecutive values. So depending on how you find your percent growth, or excuse me, your growth factor or decay factor, that's going to impact how that works in there. Okay, so let's play. Deer in a local forest have a population of 70 with a yearly growth of 6%. Write an exponential model to represent the situation after t years. Okay, so we have growth of 6%. So my growth factor is found by taking 1 plus 0.06. Okay, thinking about our equation, A equals I times, I'll put 1 plus the percent to the t. So what do we need? Ending amount. We don't know that, right? We're writing a model. So A equals initial value. Well, we started with 70 deer. So my initial value is 70. We know growth factor, 1 plus 0.06, and t years. Right? I don't know how many years have passed, but it will be t. So this right here is my model. Now, realistically, we should put these together. So A equals 70, 1.06 to the t. This here is an exponential model. Now, if we know how many years have passed, we can use this to predict future values. Okay, let's do another one. A new vehicle priced at $47,000 decreases in value approximately 12% per year. Write an exponential model to represent the situation after t years. Okay, now we are decreasing. So we're going to have decay factor. Here's my percent, so 1 minus 0.12. Okay, so again, let's think about that's where my brain goes initially. So let me just, here again is what we're dealing with. I know it's subtraction because we are decreasing, so we have to subtract. Let's plug in what we know. We do not know our ending amount, but the initial value is 47,000. Inside, I have 1 minus 0.12 t years. So again, let's just simplify. So A equals 47,000 times 0.88 raised to the t. Let's do another one. The population of bacteria started with 2 grams. And after 1 day, there were 6 grams. So I guess started day 0, we had 2 grams. Day 1, we had 6 grams. Write an exponential model to represent the situation after t days. Now, I don't have a percent increase or a percent decrease. I can see that it increased, right? So we have exponential growth. But to find our growth factor, we're going to have to take most recent divided by previous, which is 3. So this is my growth factor. So when I think about my model, this is what we had on that first page, right? Okay, so I don't know the ending amount, but initially we started with 2 grams, so that's 2. My growth factor, that's this whole piece. So I just take 3, plug it in there after t days. So you'll notice that I don't have a percent increase, right? They didn't give me that. So the growth factor is 1 plus the percent increase or recent divided by previous, right? There's 2 ways to find it. And that's how we find our growth factor to finish out our exponential model.